Predicting clinical outcomes in electronic medical records, EMRs, is a challenging task due to the high-dimensional, noisy, sparse, and heterogeneous nature of the data, as well as the limited availability of labeled data. To tackle this issue, researchers propose a novel method for automatically selecting the most relevant auxiliary tasks for pre-training from a large set of self-supervised tasks related to forecasting patient trajectories. This approach leverages a nested-loop metalearning process to learn a compact representation that can be fine-tuned on the target task with limited labels. An efficient algorithm for task selection is introduced, which yields superior predictive performance compared to direct supervised learning, naive pre-training, and simple multitask learning, particularly in low-data scenarios. Ablation analysis demonstrates that the selection rules are interpretable and can generalize to unseen target tasks with new data. By leveraging prior knowledge from related tasks, the method aims to improve the efficiency of EMR modeling. By learning representations on thousands of different laboratory tests, observations, medications, procedures, and other clinical variables for each patient over time, the authors enhance the predictive performance of clinical outcome predictions. The proposed method addresses the inefficiency and suboptimality of using domain knowledge or searching over all possible pre-training setups when dealing with abundant auxiliary tasks. The results show promising improvements in predictive performance, especially in situations where labeled data is scarce. This approach has the potential to significantly enhance clinical outcome prediction in EMRs, particularly in low-resource settings. In this research, the authors tackle the challenge of selecting and mixing the most relevant auxiliary tasks for pre-training in a multitask learning framework. They propose a novel connection between multitask learning and transfer learning within the context of metalearning. The primary task involves predicting clinical outcomes using patient records represented as multivariate time series, while auxiliary tasks are self-supervised trajectory forecasts for specific clinical measurements. To optimize the learned representation for the target task, the authors introduce an efficient gradient-based algorithm that automatically selects and optimizes the most relevant auxiliary tasks for pre-training. This proposed method is evaluated on real-world clinical datasets, demonstrating favorable predictive performance compared to direct supervised learning, naive pre-training, and simple multitask learning. The advantage of the proposed method increases in low data regimes where the target task has few labeled examples. A detailed ablation analysis confirms that the selected auxiliary tasks are meaningful and can generalize to unseen target tasks. The paper's contributions include a new approach to automatically select and mix auxiliary tasks in multitask learning, leading to better performance in clinical outcome prediction tasks. This is achieved through a metalearning framework that optimizes the selection of auxiliary tasks based on their relevance to the primary task. A nested-loop metalearning framework is proposed to guide pre-training by supervised learning on a primary outcome. The inner loop utilizes a sequence-to-sequence architecture for trajectory prediction, while the outer loop measures the utility of the learned representation via supervised learning and updates the weight of each trajectory prediction task in the inner loop via gradient descent. The framework involves a categorical choice of a particular task by learning a weight lambda to indicate the importance of each task. A basic sequence-to-sequence model is used for each task, which can be extended to more advanced attention-based or state space models. The encoder ENS theta E encodes the input sequence XF1 tau up to time tau into an intermediate state S tau, from which the decoder DEC theta D decodes the predicted sequence XF tau plus 1 tau plus H. The pre-training loss LP is defined as the regression loss between the predicted sequence and the actual sequence. For the primary supervised learning task, the pre-trained encoder is reused, and an additional classifier head is trained for outcome prediction with a cross-entropy log loss. The task selection problem is formulated as an optimization task, where the goal is to minimize the validation loss LC val with respect to lambda, subject to the constraint that the encoder and classifier parameters are obtained by minimizing the training loss LC train. The optimization process involves two loops of learning. The inner loop updates the encoder and decoder parameters via self-supervised learning, while the outer loop updates the weight lambda via gradient descent. The self-supervised learning output theta ENP implicitly depends on lambda, enabling the learning of lambda using the error signals backpropagated from the target task. The bilevel optimization process determines the quality of the learned representation from the encoder and includes two loops of learning processes. The inner loop first finds a candidate representation through self-supervised learning on the trajectory forecast tasks and then fine-tunes the representation via supervised learning on the clinical outcome prediction task. The quality of the learned representation is measured by the meta-objective of the outer loop, which updates the configuration of the inner loop to locate a better representation. The framework assumes that the self-supervised learning output theta-enp can be used as the initialization of the encoder for the target task. The normal gradient update using the train data of the target task can be used as the operator phi-train to update the initialization theta-enp. The optimization of the meta-objective enables the learning of lambda using the error signals backpropagated from the target task, allowing for the direct optimization of the generalization of the target task. Limitations of the framework include the assumption that the self-supervised learning output theta-enp can be used as the initialization of the encoder for the target task. Future work may involve exploring different initialization methods or investigating the use of more advanced attention-based or state space models. The proposed approach reformulates the implicit dependencies among parameters in the training procedure into explicit optimization constraints, utilizing a nested learning process. The goal is to minimize the validation loss of the supervised clinical outcome prediction task, denoted as LC_val, while updating the parameters of the encoder, theta-e_i, and decoder, theta-d_i, through the pretraining and fine-tuning stages. This process can be formulated as a nested optimization problem, subsequently reformulated as a Lagrangian problem with constraints. The Lagrangian L is composed of the validation loss, LC_val, and penalty terms for each step in the pre-train and fine-tune stages, using Lagrangian multipliers, alpha, beta, gamma, and delta. The derivatives of the Lagrangian with respect to the parameters and hyperparameter lambda are computed using the chain rule. Specifically, the derivatives of the Lagrangian with respect to the encoder parameters at each step, theta-e_i, and the last step of the pre-training, theta-e_np, are computed, as well as the derivatives with respect to the decoder parameters, theta-d_i. The gradients of the Lagrangian with respect to the parameters are then derived, allowing the computation of the gradient of the hyperparameter lambda. This gradient is obtained by summing the products of the Lagrangian multipliers and the gradients of the encoder and decoder parameters. The optimal conditions for the problem are obtained by setting each derivative to 0, resulting in equations, 912, that demonstrate the relationship between the supervised objective, knowledge transfer, self-supervised learning, and supervised learning processes. The proposed approach effectively propagates the signal from the meta-objective to the self-supervised learning stage and ultimately updates the hyperparameter lambda using the signals from the encoder and decoder parameters. Notably, the decoder parameter is only used in the pre-training stage and is not needed to update lambda, as verified by the optimality conditions. This reformulation provides a novel perspective on the relationship between the supervised and self-supervised learning processes, offering a new understanding of the training procedure as a nested optimization problem. Algorithm 1 presents a first-order automatic task selection method, leveraging self-supervised and supervised learning loops. The algorithm initializes parameters theta-e, theta-d, theta-c, and lambda, and iterates through the self-supervised learning loop, updating theta-e and theta-d using psi-e and psi-d, respectively. The supervised learning loop updates theta-e and theta-c using phi-e and phi-c, respectively. The hypergradient G lambda is computed using equation 13, and lambda is updated via gradient descent. To address the computational expense of evaluating equation 8, an efficient first-order approximation is proposed, treating gradients nablet theta-eilc train as constants. By applying the chain rule with the gradient approximation, the hypergradient G lambda is computed using equation 13, involving partial differential LC val, partial differential theta-ens, partial differential theta-ens, partial differential theta-enp, and partial differential LP train, partial differential lambda, obtainable via backpropagation and gradient approximation. The proposed algorithm, referred to as AutoSelect, is evaluated using the MIMICII dataset, comprising over 38,000 adult patients admitted to the intensive care unit. A set of 96 common clinical measurements is selected as candidate auxiliary tasks for trajectory forecast, including mortality, low blood pressure, and kidney dysfunction, defined using specific criteria. Predictions utilize data from the first 48 hours of ICU admission, with positive labels if the criteria are fulfilled within the next 48-hour window. In this comparative analysis, various approaches for predicting clinical outcomes in low-resource settings are evaluated, including supervised learning, pretraining, and multitask learning. The primary tasks under consideration are mortality, blood pressure, and kidney disease prediction. A sequence-to-sequence architecture with an LSTM encoder and decoder is employed, where the hidden state has a dimension of 70. For clinical outcome prediction, a simple one-layer MLP classification head replaces the decoder. Implemented in TensorFlow, all models utilize early stopping with the validation set to prevent overfitting. The results in Table 2 demonstrate that performance improves as more primary task training data is utilized. In the low-resource regime, pre-training with all auxiliary tasks outperforms naive supervised learning, illustrating the ability to transfer knowledge from auxiliary trajectory forecast tasks. However, the Mottram baseline struggles to balance the 96 self-supervised trajectory forecasts and the supervised outcome prediction task, even with additional fine-tuning. This suggests the need for more sophisticated mixing ratios to reconcile the disparate training speeds of each task. In the extreme case of using 1% of the training data, AutoSelect is compared to the two-stage pipeline approach. This comparison highlights the benefits of AutoSelect, which leverages metalearning to select the most relevant auxiliary tasks for pre-training, leading to improved predictive performance in low-resource settings. The predictive performance of AutoSelect, a novel approach for adaptively selecting and weighting auxiliary tasks in multitask learning, is evaluated through a series of experiments. Table 3 presents a comparison of AutoSelect's performance with three pre-training strategies: pre-train, top, pre-train, down, and pre-train, full. The results indicate that pre-train, top, which utilizes only the top selected auxiliary tasks, consistently outperforms pre-train, down, and pre-train, full, suggesting that the top selected tasks are highly effective in transferring knowledge to the target task. The generalization of AutoSelect across different tasks is demonstrated in Table 4, with mortality right-pointing arrow BP and mortality right-pointing arrow KD achieving high AUC-ROC scores. To understand the learning dynamics of AutoSelect, Figure 2a illustrates the training process for the mortality task, showing that AutoSelect's performance improves significantly during the pre-training stage and continues to improve at the beginning of the fine-tuning stage. In contrast, pre-train, all, does not start improving until the fine-tuning stage, and Mottram exhibits a more complex learning curve due to differences in learning speed among tasks. An ablation study is conducted to analyze the impact of different training steps in AutoSelect's nested learning loops. Figure 2c explores various configurations by adjusting the number of self-supervised training iterations, NP, and the number of inter-supervised training loop iterations, NS. The findings suggest that AutoSelect is robust across different configurations, with optimal performance observed around 150ths and 5100ths. These results highlight the efficacy of AutoSelect in selecting and weighting auxiliary tasks, leading to improved predictive performance in multitask learning. The paper introduces a groundbreaking approach to utilizing trajectory forecasts over clinical observations as self-supervised pre-training tasks, leading to substantial improvements in clinical outcome predictions. This achievement is made possible through the AutoSelect method, an end-to-end differentiable framework that automatically selects a set of auxiliary tasks for pre-training, thereby enhancing the representation learning process. The results demonstrate that AutoSelect surpasses other competing methods in terms of predictive performance on various clinical endpoints, including mortality, blood pressure, and kidney dysfunction. Furthermore, the paper explores how AutoSelect generalizes to unseen new tasks. It uses the mortality prediction task as the primary task to guide the selection of auxiliary trajectory forecast tasks, and then tests the model on blood pressure and kidney dysfunction tasks. The findings indicate that the learned weights of the auxiliary tasks are able to improve the performance of these new tasks compared to the pre-train, all, baseline. Conversely, when using blood pressure and kidney dysfunction to guide the selection learning, the predictive performance on the mortality task is slightly worse than the respective results of auto-select. In addition, the paper discusses related work in multitask learning, meta-learning, and patient representation learning. It highlights the unique aspects of its approach, such as automatically selecting a set of auxiliary tasks for pre-training, and directing the representation learning by reducing error on a downstream target task. The conclusion emphasizes the efficiency and effectiveness of the proposed method in leveraging trajectory forecasts to enhance clinical outcome predictions. The proposed architecture integrates an automatic task selection algorithm within a nested loop meta-learning process to enable efficient training of the primary task. This iterative approach selects the most informative tasks from a task pool and updates the primary task model using the selected tasks. The task selection algorithm is based on a probabilistic framework, where each task is assigned a utility score reflecting its informativeness for the primary task. The utility score is computed using the uncertainty of the primary task model on the task and the similarity between the task and the primary task. The nested loop meta-learning process consists of an outer loop that updates the task selection algorithm and an inner loop that updates the primary task model. In each iteration of the outer loop, the task selection algorithm selects a batch of tasks, and the inner loop updates the primary task model using the selected tasks. This process is repeated until convergence or a stopping criterion is reached. The authors evaluate the proposed architecture on a real clinical dataset, demonstrating its superior predictive performance, particularly in low data scenarios where the primary task has very few examples. The results suggest that the automatic task selection algorithm effectively identifies the most informative tasks, leading to improved performance of the primary task model. The use of a nested loop meta-learning process enables efficient training of the primary task model, even with limited data. Experimental results are presented in Figure 3, which shows the performance of the proposed architecture on the clinical dataset. The figure illustrates the improvement in predictive performance achieved by the proposed architecture compared to baseline methods, particularly in low data scenarios. These results demonstrate the effectiveness of the automatic task selection algorithm and the nested loop meta-learning process in improving the performance of the primary task model. This study introduces a novel method for learning patient representations from electronic medical records, EMR, data, showcasing its potential in predictive modeling tasks involving longitudinal health data. The approach could be particularly impactful in scenarios where data is limited and labeling is challenging, or when dealing with small patient populations. The authors emphasize the need to address ethical considerations associated with EMR modeling, such as biases in observational data that can propagate into predictive models. These fairness considerations are also relevant to representation learning architectures. To ensure safe deployment in clinical settings, thorough clinical safety reviews and trials across different populations would be necessary, considering issues like drift and robustness. The authors reference several studies that have utilized deep learning with EMR data, including scalable models, continuous acuity scores for critically ill patients, and prediction of future acute kidney injury. They also cite works on semi-supervised sequence learning, attentive state space modeling of disease progression, and deep physiological state space models for clinical forecasting. The code for this method will be made available on GitHub, facilitating further development and application of this approach in various healthcare contexts. Deep learning, state space models, and multitask learning are foundational concepts in the development of complex predictive models. Notably, research in deep Kalman filters, 9, structured inference networks, 10, and deep variational Bayes filters, 11, has informed the creation of sophisticated models for sequential data. Additionally, disentangled recognition and nonlinear dynamics models, 12, have been employed to capture intricate relationships between variables. Recent advances in sequential neural models with stochastic layers, 13, have enabled the integration of uncertainty into predictive frameworks. Furthermore, bi-level programming for hyperparameter optimization in metalearning, 14, as well as forward and reverse gradient-based hyperparameter optimization, 15, have facilitated the efficient tuning of model parameters. First-order metalearning algorithms, 16, have also been explored for their potential to adapt to novel tasks. In the context of clinical applications, critical care databases such as MIMICIII, 17, have provided valuable insights into patient outcomes. The sequential organ failure assessment score, 18, has been widely used to predict outcomes in patients with severe sepsis. Unsupervised time series representation learning, 19, has emerged as a promising approach for clinical predictions, leveraging the TensorFlow system, 20, for large-scale machine learning. Multitask learning has been a focus of extensive research, with notable works on automatic task selection and mixing, 21, validation of severity scoring systems, 22, and surveys on multitask learning, 23. Learning to multitask, 24, Pareto multitask learning, 25, and learning to multitask learn for better neural machine translation, 26, have demonstrated the potential for improved model performance through task diversification. Fast and flexible multitask classification using conditional neural adaptive processes, 27, and multitask self-supervised visual learning, 28, have also expanded the scope of multitask learning applications. Please provide the content to be refined, and I'll transform it into a direct, concise, and technically accurate summary suitable for voiceover narration, following the guidelines you specified. Algorithm 2 outlines the full process for automatic task selection, leveraging gradients of lambda, equation 8, as determined by alpha and beta signals. It initializes theta e, theta d, theta c, and lambda randomly and iterates through a self-supervised learning loop and a supervised learning loop. In the self-supervised loop, theta e and theta d are updated using gradient descent with respect to LP train and LC train, respectively, with Hessian and Jacobian matrices cached. The supervised loop updates theta e and theta c using gradient descent with respect to LC train, also caching the Hessian matrix. The algorithm initializes beta ns and updates it in reverse steps of the supervised loop, transferring alpha and p from the supervised loop to the self-supervised loop. It initializes the hypergradient g and updates g lambda and alpha I in reverse steps of the self-supervised loop. Finally, lambda is updated using hypergradient descent following equations 14 and 15, which define the update rules for theta e and theta c. Learning rates eta p and eta c are used for self-supervised and supervised training, respectively, including the Jacobian and Hessian matrix and cached values. The proposed algorithm is evaluated on the MIMICIII dataset, containing ICU admissions between 2001 and 2012. The dataset is pre-processed to define 4 tasks: inpatient mortality, renal failure, liver failure, and circulatory shock, triggered at 48 hours after ICU admission with a 48-hour look-ahead horizon. Table 5 presents dataset statistics, showing the number of positive, negative, and excluded samples for each task. The algorithm automatically selects the most relevant tasks for a given patient, leveraging lambda gradients to determine task importance. Using both labeled and unlabeled data through self-supervised and supervised learning loops improves performance and robustness. Evaluation on the MIMICIII dataset demonstrates the algorithm's effectiveness in task selection for ICU patients. The proposed method leverages the SOFA score criteria to define prediction tasks, focusing on positive and negative events within the prediction window. The dataset undergoes preprocessing through code harmonization, unit conversion, outlier removal, value normalization, and time bucketing. Code harmonization involves mapping medical codes from different systems to a single entity, ensuring consistency. Unit conversion is automated with manual review, identifying outliers as values below or above specific percentiles. Value normalization is achieved via z-scores, using the mean and standard deviation of the cleaned dataset. Time bucketing averages multiple measurements within a 1-hour time step for each clinical feature. The preprocessed dataset includes 96 frequently occurring lab measurements, vital signs, and interventions, equipment settings, detailed in Table 10. Hyperparameter selection is performed through validation, optimizing the validation AUC in MSE. The selected hyperparameters are listed in Table 6, including learning rates for supervised and self-supervised learning, lambda update, and LSTM state size. The authors evaluated the predictive performance of 3 methods: supervised pretrain, all, co-train, and auto-select on 4 primary outcome prediction tasks: mortality, shock, kidney failure, and liver failure, under varying levels of data scarcity. The results, presented in Tables 7 and 8, show the area under the receiver operating characteristic curve, AUC-ROC, and average precision, AUC-PR, of each method at 1%, 10%, and 100% data scarcity levels. Auto-select outperforms both pre-train, all, and co-train by a significant margin in low data scenarios for all 4 tasks, achieving higher AUC-ROC scores across all tasks and data scarcity levels. The largest improvements are seen in the low data scenarios. For hyperparameter tuning, the authors employed a grid search to jointly optimize the learning rates of all training loops and the state size of the long short-term memory (LSTM) network. The considered hyperparameter values and final selections are listed in Table 6. Notably, auto-select's superiority in low data scenarios is further supported by its predictive performance on an additional task, liver failure prediction. The authors' experiments demonstrate the effectiveness of auto-select in addressing data scarcity challenges, highlighting its potential in real-world applications where high-quality data is limited. For each primary task, the top trajectory forecast auxiliary tasks are identified in Table 9, which highlights the most critical features associated with each task. In mortality prediction, key features include invasive and non-invasive blood pressure, anion gap, heart rate, respiratory rate, and minute ventilation observations, among others. Similarly, shock, kidney failure, and liver failure prediction rely on a common set of features, including invasive and non-invasive blood pressure, heart rate, and respiratory rate. Table 10 provides a comprehensive list of input features used in the model, including harmonized names, display names, mimic codes, LOINC codes, units, and count. These features range from access pressure and albumin levels to arterial base excess, arterial bicarbonate, and arterial pH, as well as blood flow, basophils, and bilirubin levels, among others. These carefully selected features capture relevant information from the patient's medical history and vital signs, enabling the model to make accurate predictions about patient outcomes. By learning to predict the top trajectory forecast auxiliary tasks for each primary task, the model leverages these features to identify critical patterns and relationships that inform clinical decision-making. The model incorporates a comprehensive set of input features, encompassing various physiological parameters and lab results. These features are meticulously listed in a table, providing harmonized names, display names, mimic codes, LOINC codes, units, and counts for each parameter. Notable features include blood pressure measurements, both invasive and non-invasive, as well as cardiac output rate, cardiac index, chloride levels, CO2 levels, creatine kinase levels, creatinine levels, central venous pressure, CVP, eosinophils percentage, and exhaled minute ventilation. Each of these features plays a critical role in understanding patient physiological status and lab results, which are essential for developing accurate prediction models in healthcare applications. The inclusion of these features enables the model to capture a comprehensive picture of patient health, facilitating the identification of complex patterns and relationships between physiological parameters and lab results. The harmonized naming convention and standardized coding systems, MIMIC and LOINC, ensure consistency and interoperability across different healthcare systems and datasets. The table provides a detailed breakdown of each feature, including units and counts, allowing for precise interpretation and analysis of the data. This level of detail is crucial for ensuring the accuracy and reliability of the prediction models, as well as facilitating the identification of potential biases and limitations. The comprehensive set of input features is a key strength of the model, enabling it to capture a wide range of physiological and lab-based parameters that are critical for understanding patient health and developing accurate prediction models. Table 10 presents a comprehensive list of 25 input features used in the model, including various physiological and laboratory measurements. These features include exhaled minute ventilation, expiratory ratio, FiO2 analyzed, glucose, heart rate, hematocrit, hemoglobin, INR, inspiratory pressure, inspiratory time, inspiratory ratio, ionized calcium, ketones urine, lactate, lymphocytes differential, magnesium, mean corpuscular hemoglobin concentration, mean corpuscular volume, minute ventilation observed, monocytes, neutrophils urine, and O2 flow. Each feature is accompanied by its respective unit of measurement, such as L_per_min for exhaled minute ventilation, ratio for expiratory ratio, and mg_per_dl for glucose. The count column denotes the number of instances for each feature in the dataset. This table provides a detailed overview of the input features utilized in the model, which is essential for understanding the subsequent results and analysis presented in the paper. The comprehensive list of input features used in the model consists of 35 distinct variables, each with its harmonized name, display name, mimic code, LOINC code, unit, and count. These features encompass a wide range of physiological and laboratory parameters, including oxygen saturation, blood gas values, respiratory rate, and blood cell counts. A detailed mapping of each feature to its respective codes, units, and count ensures consistency and standardization across the dataset. For example, oxygen saturation is represented by three codes: 50,817, 646, and 6,719 with units in percent, while platelet count is represented by two codes: 227,457 and 3,789 with units in K_per_ul. The inclusion of these features is crucial for developing a robust model that can accurately predict patient outcomes. By standardizing these features, the model can effectively leverage the relationships between these variables to make informed predictions. The count column provides an indication of the number of instances for each feature, which can be useful for identifying potential biases or imbalances in the dataset. Thorough documentation of these input features is essential for ensuring transparency, reproducibility, and generalizability of the model. By providing a clear and comprehensive understanding of the input features, the model can be better interpreted, and its performance can be more accurately evaluated. Table 10 presents a comprehensive list of input features used in the model, comprising 12 distinct variables. These features include vital signs, laboratory results, and clinical measurements such as ultrafiltrate output, sodium levels, mixed venous oxygen saturation, total bilirubin, temperature, troponin T, urine output, and tidal volumes. Each feature is associated with multiple display names, mimic codes, LOINC codes, units, and counts. For instance, the feature RRT output at ml has multiple display names, including ultrafiltrate output, dialysis out, and dialysis output. Similarly, the feature SVO2 at percent has display names such as SVO2, mixed venous O2% sat, and SVO2. The mimic and LOINC codes are provided for each feature, enabling standardized identification and mapping of the variables. The units of measurement are also specified, such as MEQ_per_L for sodium levels and ml_per_breath for tidal volumes. The counts column indicates the number of observations or measurements for each feature. For example, the feature urine output at ml has a count of 252,169, indicating that there are 252,169 observations of urine output in the dataset. This table serves as a reference for the input features used in the model, providing a detailed description of each variable and its corresponding metadata. The harmonization of feature names and the provision of standardized codes enable efficient data integration and analysis. The features listed in Table 10 are essential for modeling and predicting patient outcomes in a clinical setting. The inclusion of vital signs, laboratory results, and clinical measurements provides a comprehensive understanding of patient physiology and enables the development of accurate predictive models. The standardized representation of these features facilitates the application of machine learning algorithms and the derivation of meaningful insights from the data. Table 10 presents a comprehensive enumeration of the input features utilized in the model, providing a detailed overview of the harmonized names, display names, mimic codes, LOINC codes, units, and counts for each feature. The table lists 842,129 instances of WBC count, represented by various display names, including WBC, white blood cells, and WBC, 411,000, with corresponding mimic and LOINC codes, and units measured in K_per_UL. The weight feature is represented by the display name daily weight, with a mimic code of 224,639 and a LOINC code of 763, measured in kilograms, and a count of 93,386. The inclusion of this table ensures transparency and reproducibility in the author's approach, allowing other researchers to replicate their methodology and build upon their work. The comprehensive enumeration of input features is essential for understanding the model's architecture and its ability to process and analyze the input data. The table provides a clear and concise summary of the input features, facilitating the replication of the study and enabling further research in the field. The table's organization and content demonstrate the author's attention to detail and commitment to transparency, allowing for a clear understanding of the model's input features and their corresponding codes, units, and counts. This level of detail is crucial for ensuring the accuracy and reliability of the model's results, and for enabling the development of similar models in the future.